Hello everyone, welcome back to lecture 10, and this will be the last part of lecture 10 where we will look at a case study for exploratory spatial data analysis. In the past, in the last couple of lectures, what we did was we started with a coal mine sample data set where we had sample locations at in a given datum or in a given region, and the idea was that everywhere we do sample we see percentage coal ash. Everywhere we do not sample we do not know what is happening beneath the ground. So we said, look, ultimately we would like to sort of understand the coal quality for the entire region, but where we start is by summarizing the data or conducting what we call as the exploratory spatial data analysis. Why is it exploratory spatial data analysis and not just exploratory data analysis? Because the data themselves are spatial in nature. They are delineated with a latitude and a longitude coordinate system, or it's just something that we saw in the last lecture, a row column two-dimensional coordinate system. Broadly we looked at three strategies. The first one was a histogram, right? We saw a earlier version of the histogram which we called as the stem and leaf plot, right? And the major idea of conducting exploratory data analysis or this kind of summarizing data that we covered last time was called detecting outliers. Right? So we looked at the shape of the histogram. Is it a skewed distribution? Is it a symmetric distribution? If it is skewed, in what direction? That gave us an idea, okay, there may be some values that might be quite large relative to majority of data, or the other way around, some values might be very, very small relative to the majority of data. Okay? So histogram was the first starting point, but histogram by itself does not or did not appreciate the spatial nature of the data, right? So the second thing that we looked at was this statistic called mean minus median and its absolute value, which we defined as something called as the U statistic, right? And this U statistic was calculated by rows and by columns. So now we sort of constructed this spatial statistic that helped us detect outliers. And we said that, look, if mean and median are too far apart, then we should be worried. And we in fact sort of figured that if U was greater than 3, then that's the point where an analyst should become worried about outlier values. The third strategy or major device that we learned last time was based on this idea of local stationarity, right? And this basically was a bivariate scatter plot of observed coal quality realizations in a local neighborhood, right? So if I observe that 10% of the coal content is ash at location A, if I go one step further in either direction, either north or south, east or west, I should expect to see a similar value to 10% coal, right? If I start seeing something like 20% all of a sudden, then that should sort of provide me some sort of alert signal that maybe I'm looking at an outlier value in this domain or in this small local region, right? So today what we are going to do is that we are going to take this machinery that Cressy provided us to conduct exploratory spatial data analysis and apply it to the administrative groundwater level data for India, right? More specifically, we are going to look at the data that are provided by the Central Groundwater Control Board, right? And we are going to apply the machinery of exploratory spatial data analysis and try and detect outliers through the 3 devices that we discovered last time. Okay, so let's look at the data and move forward. Okay, so I'm just showing you a figure of Uttar Pradesh, so you can sort of guess that we are looking at the administrative boundary of Uttar Pradesh state, which is in pink color, right? And the dots that you see inside the Uttar Pradesh region or Uttar Pradesh state are groundwater monitoring wells installed by the Central Groundwater Control Board. Okay, so now this Central Groundwater Board that is trying to monitor values, every year, what's happening before monsoon, what's happening after monsoon, what's happening right after the harvest of the Rabi crop or the Kharif crop. They basically have to go in to each of these, wells, go in and figure out what is the depth of groundwater level at each of these wells. And whenever you have groundwater depleting or the level of groundwater depth going down quite a bit, that provides a signal to the Central Groundwater Board that you must intervene in order to control this decline in groundwater levels, right? If you watch news or if you are generally interested in social issues, you would know that groundwater depletion is indeed a very serious issue in India today, right? There are multiple agencies, there is not only CGWB, which is the Central Groundwater Board, but there is also an Uttar Pradesh Groundwater Board, which which is a body which tries to monitor groundwater levels across state, right? So both the central agencies and the state agencies in India have their own network of monitoring groundwater levels because this issue is so important. Right now, in this picture, there are dots. There are these pointers which are giving us location of groundwater monitoring wells. Right. So these are wells these are owned by the agency, meant to monitor groundwater levels. Remember, they are not meant to be drawing water for consumption, either for domestic use or for agricultural use or for industrial use. They are only for the purpose of monitoring the groundwater data. Okay, these are color coded, for this year 1998. Sorry for the typo on that slide. This is for the year 1998, and the green colors are wells where the situation of groundwater depletion is not so alarming, right? So we have, the dark green is where the groundwater level goes below the ground about 2.5 meters. We are fine. And then, as we go further, there are some wells which are color coded red, where, the groundwater levels have gone down up to 32.8 units, right? So these are the wells where, which should provide some kind of, management intervention from the agency. Now, very low values and very large values are obviously, candidates for, for detecting outliers. The very low values could be an outlier, very high value could be an outlier, right? Now, if I look at this data, right, if I visualize this data, I see a lot more dark greens and light greens and yellows than I see oranges and reds. For sure, reds are, you can count them here, like probably there are 10, wells in 1998 that showed very high depletion, right? So if I were to sort of imagine a histogram for this, for this case, the minimum value the well depth can take is 0, and it can go up to 32.8. So I'm going to make it 33, and most of the values are between, let's say 0 to 6 in the first two categories, and there are some which are going up to 10. So 0 to, let's say 3, 6, some of them are also going to 10, right? And very low ones are going to the other ones, right? So we have a situation where, you know, most of the data lie between 0 to 10, and after that we have some values which are going up to 33 or 32.8, right? So this is the sort of, you know, understanding of the distribution of groundwater levels for Uttar Pradesh. Okay, so now it's clear that if I'm going to find outlier values, they're going to be coming from, you know, greater than 10, most likely, right? But we saw last time that we should be careful. We should, you know, of course, whenever I see values greater than 10 or greater than 15 or 18 for that matter, that should definitely, you know, create some kind of a you know, alert. But in general as well, like, you know, if I see values greater than 10, I should be, you know, starting to detecting outliers more formally than just looking at, you know, a histogram or the visual picture. So let's move forward. So we saw last time that in the Cressy's machinery, the data were organized in the row column, you know, in row column fashion. Now, in order to do that, we what I do here is that to the map of Uttar Pradesh, where I have many wells scattered around space, and the spatial distribution is not consistent. Now, this is not textbook data that I will find a very nice characterization where data will be, you know, exactly collected in a nice grid cell of rows and columns. But I have to make an attempt to organize the data in that fashion so that then I can apply the machinery that Cressy has given me, right? Okay, so we apply this grid cell formulation and we try and organize data in this, you know, in this format to move forward. Okay, so we have to apply an intervention to the given raw data set and then, you know, to be able to move forward with the textbook methodology that we have seen till now. Okay. So for the purpose of this, lecture, we will look at a very small area. We will not look at the entire state because, you know, it will be a lot of data and hard to sort of, you know, bring together for the pedagogical purposes. So we'll focus on a small cross section in, you know, sort of near to central to eastern Uttar Pradesh. So I've shown you a zoomed in version of this little cross section, and what we see here, I mean, we observe a few things. The first thing that you observe here is that many of the cells have no values, have no monitored values, right? So this is real world data set. If we don't have a value in a cell, well, we don't have a value in that cell. We can't do anything about it, right? Now, Cressy's methodology doesn't necessarily exclude this kind of a situation. If you saw, although most of the data were nicely, you know, organized in the row column grid network from the previous lecture, there were many of these grids that were empty, right? So we can now, even with this situation, real world situation, we can move forward with Cressy's methodology, right? But another thing that we see here, which is much more critical, is that some regions in this cross section seem to be much more highly sampled than others, right? For example, you know, if I look at you know, this region in green, circle, there are two regions that I am able to find which seem to be more densely monitored by the monitoring agency, that is Central Groundwater Board, than other regions, let's say on the east of this cross section, right? Now, there are many reasons why this can happen, right? It is possible that there are some regions that require more intense monitoring, right? Some regions that are more prone to, you know, depletion of groundwater, and hence the monitoring agency decides to go in and monitor that region more closely, right? There are other regions that may be, you know, even remote. I mean, it's possible that it's a forest patch or it's a water body that, you know, I can't, you know, naturally, due to natural constraints, can't really monitor. If that is the case, I'm not going to find too many wells in that region, right? If the river Ganges is flowing through a particular region, you're not going to find, you know, monitoring wells in the middle of river Ganges, right? So there are natural constraints. There could be monitoring requirements that can drive how different regions are monitored, across space, especially for groundwater. And they may not follow the nice schematic, textbook schematic that Cressy had provided us, where you had equidistant sort of monitoring sampling locations distributed across a datum for the most part. Okay, so if I come back to this zoomed in version, I see that there are some cells which have two observations, and I'm just going to try and mark these cells for your benefit here, right, where I'm able to see some cells with more than one observation filled in. So these cells basically are containing more information than their other counterparts, right? So what is the consequence of this kind of a sampling methodology? So we are going to sort of learn about something called a sampling bias, in the sense that some regions are more densely monitored or sampled than others, right? And this can possibly introduce bias to our samples. And before we go ahead and use these data for summary statistics, for doing calculating the U statistic, that is the mean minus median absolute value, we should do what is called as declustering of this data. That is to be able to make comparisons which are apple to apple comparisons, right? Just because you have 3 monitoring locations in a given cell, shouldn't favor you in some way in terms of the value that you are able to provide, versus other places where you have only 1 observation or no observation at all, right? How do we create a balance so that when we are when we are comparing the means of values in a given cell with 2 observations versus 1 observation, remain an apple to apple comparison rather than apple to oranges comparison? Okay, so let me first sort of go through this idea of sampling bias and cell declustering, and then we will apply this to this data and then move forward to conducting the analysis. So the idea is that I cannot move forward with the analysis till I have intervened and applied cell declustering to a real world data set, right? So this is an extra intervention that this real world data set demands. So let's define this situation. At times, while using real world data sets, we encounter situations where sampling density is higher at some locations or localities or regions than others. Okay, and of course, there may be multiple reasons. I mean, the reason could be access or convenience, right? Just because it's convenient for me, I can sample that required location. As a researcher, so it's a subjective sort of bias might enter through the person who is sampling data, right? So there could be this kind of a bias. There could be, in case of groundwater, there could be things like crisis, community attention, and even media can drive sampling of groundwater levels, right? So especially if you have a lot of attention from the community because the groundwater levels are declining and we will not get water in the future, and it is possible that the monitoring agencies can intervene and start to monitor those areas more intensely. Now, what that will do, if you try to visualize that situation, that last example that I gave you, if we try to visualize that, what will happen is that there's going to be a very large sort of density of, samples in an area where the water levels have declined relative to ones where they may not have, declined as much, right? So you can have a situation where you have a region where such that high values are sampled more vigorously than low values, right? In that scenario, if I were to take a sample mean, if I were to just take a mean of values, through the datum without this consideration why some areas are more densely sampled than others, I'm going to underweigh the regions which may not be under crisis and overweigh regions which are undergoing depletion at a faster rate. And the overall picture will come out seeming like, oh, there is so much crisis, right? Whereas what we've done is that, where we have, in this H region where we have so many sample locations, if I add one more, I'm not really adding any more information. But relative to that, if I were to add this monitoring well, these two monitoring wells in the low region, I will get much more information, right? So that's the crux of this disproportionate sampling, distribution in space, right? And the kind of bias that this issue can bring, right? So here, obviously, H values are overrepresented, and L values are underrepresented. Correct? Right? So if I take a sample mean, if I just take a mean without being cognizant of this disproportionate issue, I'm going to have a biased understanding of the situation in the real world that I'm trying to study. And it could be anything. It could be development outcomes, it could be education levels, it could be crime rates, it could be, groundwater levels as we are looking at it. It could be deforestation. It could be many different, contexts that one can study these issues, right? So the methodology that we are studying is much more general, right? Okay. So the solution to this problem. So the solution to this problem of sampling bias, where bias is introduced due to how we sample data, is called as cell declustering. Okay, what is cell declustering? So cell declustering, for understanding that, let's actually draw a figure which is quite similar to the real world situation that we are facing with our data set. So we have a grid cell right, where we have sampling locations distributed across these cells, right? Some of these cells, or most of these cells, you can say will have one observation, but some of them can have more than one observation. Okay, so I'm going to simply try and okay, let's say this is the data set that I have. Some of the cells are empty, not represented. Some of the cells are represented by one sample location, and some other cells are represented by, even a situation where you have 6 sampled locations. Okay, so we have divided this area into a grid. That is great. So we have, let's say, total of capital N cells. Okay, and the number of data points that are observed in each of these cells can be, let's say, denoted by a letter C. C observed. Okay, C observed. Right now, what you can do is, let's say you have a a total of t data points in the entire domain, right? So, total t data points in the entire domain, right? In total, right? C0, or let's say not C0, let's call it Cn. So, I'll just give it a notation of small n, just a second. Okay. Cn is the number of observations or data points in each cell, that we are looking at. Okay. Then define a weight at each location, let's say Sj, right. So, this is cell j, right. So, jth cell, I have this weight that I am defining. I could in fact just call it Wn, right, Wn, and this will be equal to, I am going to define this weight as Ct over n. So, this is the total number of cells, total number of observations per cell that I should expect if the data were uniformly distributed. And this is going to be now weighed by the number of cells that I actually observe. Okay. So, this is the ideal, this is actual, right. This provides me a weight that if I apply to each observation in this cell, right, each observation in the cell, then I will get a declustered value. Okay. So, declustered data values will be Wn Zn. This is the weight, right, for cell n, and this is Zn is the data observation in cell n. Remember, for the cases where you have just one observation, this weight will be higher than for those cells than the cells which had more than one observation. So, Wn will start to discount for the density of observations in highly sampled cells, right. So, the fact that you might be over representing H regions will be discounted or normalized by this Wn weight, right. So, using this weight, we can then define our summary statistics. We can say the declustered mean. What would be a declustered mean? It will be Z bar equals summation I equals 1 to n Wn times Zn divided by I equals 1 to n, or let us say n equals 1 to n Wn. Okay. Similarly, we are going to have, we can also define, so this is sample mean. I can also define sample variance. Let us say this will be S squared equals summation n equals 1 to capital N Wn Zn minus Z bar. Remember, Z bar is the declustered mean, okay, divided by summation n equals 1 to n Wn minus 1, such that summation n equals 1 to n Wn should be equal to. Okay. Similarly, you can define sample covariance. Okay. So these are the summary stats that we typically evaluate with the data, right? So we have again summation n equals 1 to n Wn z, or here it's x, so I'm going to use xn minus x bar. Again, x bar is the declustered mean, right? Yn minus y bar. X bar and y bar have to be equal because they are declustered means for the same region. I could in fact use z bar instead of these values, right? Over summation n equals 1 to n Wn, right? Now, I have been able to now construct, declustered means, mean values or summaries or data-based statistics, which will not be impacted by disproportionate sampling in space, right? Now, a question that would arise is, what is a good cell size, right? What is a good cell size? Now, there is no real theory for what should be the right cell size. So let's just go back and let me show you. I mean, it is possible that I could have, instead of using the cell size as you see in the on the screen, I might have, instead using larger cells, right? I mean, I could have combined 4 cells into one and created a grid network that looked much bigger, right? So, and if I do that, then my problem sort of becomes a little different, right? I mean, my number of total cells will differ, the number of, observations in each cell will differ, and so on and so forth. So my entire analysis is conditional on the size of cell that I choose. So there is no theory for choosing these, cell sizes. The best strategy is to visually analyze whether, in sparser regions, we are able to capture, let's say, one data point, right? And in denser regions, we are still able to, sort of get into, individual data points other than, encompassing a lot of data points at once. With larger cell sizes, what would happen is that I will have some regions which will sort of start to encompass so many data points, and most of the other regions will have nothing, right? That is why maybe larger cell sizes may not be optimal for the case that I am working with, right? So it's really an analyst's judgment what should be the right cell size. But the point that I'm trying to make here, which I want to sort of drive home, is that when you work with a real world data set of your choice, of your interest, then the best practice would be to make sure that you decluster these data points. Otherwise, sampling bias will enter your analysis. Okay, so now having understood this, we will now move forward and apply Cressy's machinery and try and discover outlier values for our data. So let's apply Cressy's machinery here. Each cell has now the declustered mean, right? So if you had 2 observations in a cell, you have the declustered mean value inserted in this cell, right? This looks very similar to the XY, column row, representation of the Cressy's data that we looked at. In this data set, we have 37 rows and we have 22 columns, right? So we have rows which are represented by the x-axis, something that we saw in the previous lecture as well. And then we have, the columns on the x-axis, right? So rows on the y-axis and columns on the x-axis. Now let's look at the makeup of the data. Remember, we looked at the entire UP region data set, and there the outlier values were sort of, greater than 10, or, we should be alerted, we should have been alerted, we saw values greater than 10, certainly if we found something greater than 18. Remember, this is not the entire UP region data set. I'm looking at a small cross section, right? So if I'm looking at a small cross section, you know, I should be sort of cognizant that I cannot apply the same summary stat that I sort of applied or I you know, earlier. So I should do a new stem and leaf plot or a new histogram to get a sense of these cutoff values where I should be, you know, alerted for outliers. But still I can make a start, you know, I can just look at the data. And what I see here is in the first column, I see 11.13, 16.84, pretty high values, 1.95, again, a very small value, 4.58, 1.97. In the second one, I see 12.5, 5.9, 7.02, 9.3, 4.1, 2.2, 8.9, and so on and so forth. The entire mix of data set, it seems to me that if I see a value greater than 10, I should still get worried, right? Because I don't see too many large values here, right? So if what I see is a lot of 3s and 4s and maybe 6s, but there are some, you know, 12.3, there is a 10.5 all of a sudden, right? So those sort of those values sort of should sort of ring a bell that, you know, maybe something is off here, right? So let's move forward and let's do these mean and median summaries to get that sense. Okay. Now we know that if mean and medians are far apart, that's the first signal that, you know, there may be outlier values to look at. These are the mean and median summaries across latitudes. So the latitudes are my rows, right? If I go back, sorry, these are my my columns. So you know, I'm looking at longitudes, which are 37 rows and 22 columns. So if I have data, you know, okay, so it's across rows and it's across longitudes, not latitudes, sorry about that, right? And my median is represented by a green circle, whereas the mean is represented by a you know, a cross of red color. There are areas where the mean and median are quite close to each other. Those are non-troublesome areas, but there are other areas which I should start to worry about, like for example, row number 6, row number 29, you know, row number 2, row number 3, and so on and so forth, right? Wherever I have these issues, you know, I will have to go back and look at my data again for outlier values. Okay, so I'm going to say, I'm going to mark rows, let's see, 3, 6, 29, 31, right? Where else do we see a very large difference between the two? Maybe here we see a very large difference at 33. Okay, so we are going to look at 3, 6, 29, 31 and 33. Okay, we'll try to remember that when we get there. We'll just do a recall. Okay, now this is across columns. We have 22 columns. Now again, mean is in red, a dead dot, median is a green dot. And here, you know, there are many columns where things look okay, you know, things look all right to me, right? But there are many other columns where things don't look okay. So for example, column number 2, column number 8, column number 9, column number 13. So I'm going to write that down, columns 2, 8, 9, 13, 20, right? I should probably also check all these other columns, right? I mean, they're not exactly quite small. So you have 14, 15, 17, all right, and maybe this one as well, number 6. Okay, so I'm going to make a case for you know, I'm going to recall them when I go back to the data set, and I'm going to look at these columns again carefully. Okay, I'm back to my data set. So here what I am you know, providing you is a you know, a U statistic for columns. Okay, so for columns, if I go back, you know, what seemed problematic was 2, 8, 9, 13, 20, 14, 15, 17, 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9 columns looked problematic visually. Let's go back and look at the U statistic and see which ones are actually problematic. It turns out most of the columns are fine. There are only 2 columns and maybe one more right here, which is 2.78, which I should probably pay attention to. right? So among these 9, 8, 16 and 18 are problematic, right? So in my visual analysis, there is 8, there is 16, I don't even have 16, I don't even have 18. So maybe, so this one was more problematic than the one that I picked, right? So this is the reason why you should do, a summary statistic, right? Or use the U statistic, because the U statistic is not about just the difference, but also the variance of the difference. Especially in case of row 16, right? If I go back and if I look at row 16, I have a value of 2.78, right? U is y bar minus y tilde over variance of y bar minus y tilde, okay? Mean minus median over the variance of mean minus median, right? Oh, sorry, maybe the standard deviation, the square root of the variance, right? Now, if I look at 15 and 16, if I go back and look at 16 and I look at 15 and look at 17, the value of y bar minus y tilde seems to be higher for both 15 and 17 than it does for 16, right? But the U statistic controls for the variance as well. So it turns out that although 15 and 17, rows 15 and 17 have higher numerators, they also have a very high denominator. Whereas in case of 16, the numerator is small, but the denominator is proportionately even smaller. That's why this row, this column turns out to be more problematic. Let's look at these columns where U is greater than 3, right? So this is U greater than 3, U greater than 3, U is less than 3 but close to 3. So I'm just, as an analyst, I am a little bit more conservative and I want to be careful before I reject something. Okay, so here I have 2.72, 2.2, 0.68, 8.03, 1.44, 12.71, 2.05, 2.56, 1.78, 4.55. I would, circle the high values of 8 and 13 or 12.7 as potential outliers. Okay. Similarly, I can go to row 18 where the U is definitely greater than 3, but it's probably the highest. So I have 2.3, 3.5, 1.8, 2.42, 3.71, 0.8, 2.23, 3.55, 10.5. So I arrived at a high value working through this column, 2.3 and 3.17. That's another candidate for a outlier, right? Now let's look at this little, problematic, seemingly problematic row, column, which is 16, 1.6, 3.9, 4.8, 1.4, 0.53, 1.1, 0.842, 1.47, 1.15, and 2.05. Indeed, I'm not able to find a value which I should probably be concerned about. So, U less than 3 seem to work for me, all right? So I'm going to move forward with these 3 candidates of outlier values. Before I move forward, I'm going to now give you a homework where you should, conduct the mean minus median analysis for rows and point out the outlier candidates. Point out the candidates for outlier values. Okay, obviously this is not going to be a graded homework, but this is very important for you to practice. Look, you have the data in front of you on the screen, you have the methodology, just apply for practice, right? This is practice. Okay, so I'm going to move forward and I'm going to look at these plots, right? These bivariate scatter plots between ZS and ZS plus E, right? Now these are across columns, so this is north to south. So I'm going to stand on a location, I'm going to go one step north, right? And create a counterpart of ZS as ZS plus E, right? Here, now, remember, when we think about it, we try to find a core, we try to imagine a normal distribution in space, and then think about the outlier values. It seems like the core is somewhere here, or maybe like even downward, and the distribution is sort of going to sort of fall down from 0 further on, right? So I think the values that are lying outside, far apart from this cluster of data, are good candidates for outlier values, right? So I should go back and check all of these ZSEs and see if they fit the bill to be a outlier value. Okay, all right. Okay, these will be here, and so on and so forth. So this is now, okay, so the previous one was west to east, this one is north to south. Sorry, I kind of gave you a different understanding earlier. So the previous one was west to east and not north south, but this one is a north south. Okay, all right. So that's about it. So I've not really given you the outlier values. I'm still leaving it up to you to figure it out by yourself and complete this process and come up with the candidate outlier values that you should be worried about when you report the mean of this data, the variance of this data, the standard deviation of this data, and so forth, so on and so forth. Okay. Next, in the next lecture, we are going to cover this concept of spatial stationarity, right? Spatial stationarity is a very critical concept of spatial statistics, and if we are to define a mean, a variance, or anything about a data set, we should first resolve spatial stationarity. All right, so look forward to having you in the next lecture on spatial stationarity. Thank you very much for your attention.